Okay, for this problem, I will draw it again for the case of the axis. Okay, so the ball is moving along the circular path here, and we have the center of curve here. So then normal direction is over here. This is normal direction. And so the tangent direction should be perpendicular to normal direction here. Okay, and it is not the same as the R in the interior. This is fixed points for polar coordinate system. So then R is over here. This is R direction. Okay. And for theta direction, it should be over here, right? And the problem would like to determine the force of the arm OA acting to the ball. Okay. This means that the force that arm OA acting to the ball is mean it is a force here. And it is the same. It is perpendicular to the arm, right? So then it is the same directions of theta. So then we would like to find this force that is in theta direction, not in normal and in tangential direction. So then that's why, and according to the problem that's given us, the value of omega and value of alpha, sorry, the value of alpha and omega. Okay, omega is the angular velocity, and alpha is the angular acceleration here. Okay, so because we use this value, we know this value, so then it may be more convenient to solve this problem in theta coordinate system. Okay, so we starting with draw the free body diagram and kinetic diagram. To draw free body diagram, okay, we may draw free body diagram like this picture on the left hand side, and kinetic diagram we draw on the right hand side. And you see that we have to set up acceleration in both sides in the same directions of r and theta. R is in this direction and theta is in this direction. So then for theta direction, this is positive direction, and for r direction, this is positive r direction. Okay, and according to this picture, okay, so we can adding something that is this angle, it should be theta, right? Or it is the same angle. Okay, and according to this, we can set up for the equation of motion that we may starting with the kinematics first. From the previous topic, we can determine the acceleration in r and in theta direction by take the first and second derivative of r. Okay, do not forget to use the chain rule. Okay, and then we obtain acceleration in r and in theta direction over here. And then we form the equation of motion in r direction and also in theta direction. Okay, so according to this, we have this is angle theta. Okay, so when we decompose ns into r direction, that is over here, this is r direction, and perpendicular to this is theta direction. Okay, and this is the normal direction here, and also this is tangential direction. Okay, In this case, we will form the equation of motion in terms of I in theta, r theta instead of x, y, and nt. Okay. So according to this, for the forces in r direction, okay, we have the equation of motion of this case, okay, and the weight of 0.5 pounds, okay, divided by the gravity, okay, that is 32.2 foot per sec square. Okay, we change to be the mass, okay, and then come up with the acceleration. Okay, acceleration is negative because we already determined the value of the acceleration in r direction, right? In r direction, that is negative value. And we substitute into the equation of motion for r direction, and then we obtain ns, that is 0.279 pounds. Okay, ns is the normal force between the ball and the part, not the arm OA. Okay, and then after that we consider the equation of motion in theta direction. Okay, so for in theta direction, we have the angle theta here. Okay, we have the angle theta here, and then we form the equation of motion in theta direction, that is in this direction, right? Okay, so what does it mean? Okay, so it found out the angle theta is over here also. So then we have the summation of force in theta direction is like this, and on the right hand side is the MA, and we use the acceleration in theta direction, and we can determine for N over A is over here. Okay, it's positive. It means that it is in the same directions of the theta. Okay, so that's all of this problem. Okay, that's all for this problem.